A2 series. Today we'll be starting the topic of circular motion, which is the first chapter in the A2 physics series. So what is a circular motion? Well, the name really suggests it all. It is any object that is revolving in a circular orbit, which means that this object starts from a particular point A and its journey ends at that same point A, right? So it looks, the path or the trajectory would look something like this. Now, we can define a center of this circle and we can draw a radius vector, call it R, from the center of the circle to the object. And that's your radius vector R. Now, you can measure the angular displacement from this center of the circle that this object would travel. So maybe this is your reference line, and then you can measure this angle, and this angle would keep on changing. True, right? So for example, when this object was at this point, you would have a particular value of theta, and then it moves to this point, then the radius vector will be pointing like this, and the particular value for theta would change accordingly. So it would be something like this. Let's call it theta prime. So that's basically what circular motion is, right? Now, we can measure this angle theta in different ways. We are familiar with the degree measurement, right? So we know how to measure angles in degrees. And so we say that when an object starts its journey at point A and it travels all of this distance and comes back to point A, we say that it has covered the angular displacement of 360 degrees. So this is one complete revolution. Now, this angle measurement in degrees is, there's no specific reason why we say that this, when an object starts its journey from point A and ends at point A, there's no reason to say that this is 360 degrees. So there was no specific reason in defining it as to be 360 degrees, splitting the circle into 360 degrees. It may have arisen from the approximate number of days it takes for the Earth to orbit the sun. So we can define another measurement for angle, which is known as radian measurement. Now, a radian measurement is simply defined as the ratio of the arc length to the radius. So for example, this is the center, and at some point, the radius vector points like this. So the object was here, and suppose it moved some distance and the radius vector now points like this. So it has covered some angular displacement theta from here to here. And the arc length is really this thing, this path or this trajectory that it covers. Now, 1 radian is defined as the ratio of the arc length of this path divided by the radius of the circular path. Now, this just means that a radian, 1 radian, is the angle that is subtended at the center of a circle by this arc, which is equal to the length to the radius, right? Now, the circumference of this circle that it covers, we know that for a circle, the circumference is 2 pi r, right? Now, here, this thing r is the radius, and 2 pi is the complete angle in radians, right? So it is the complete 1 revolution in 360 degrees. So that's your 2 pi. Now, this means that 360 degrees is equal to 2 pi radians. This definition of angle also comes from this definition of radians. And so I can then say that my 1 degree is really equal to 2 pi by 360 radians. Right. So that's your discussion about radians. And now we can really, let's draw a circle. So for example, if I have something that looks like this, and here is the center, and this is the radius vector. So the object was here initially, and then it covers some distance and comes to this point over here. Now we can talk in terms of what is known as the angular displacement. And the angular displacement is defined as this angle that it covers from its initial position I to the final position F, right? While this is the radius vector. Now this angle theta is preferably measured in radians. And as we move along, we'll see why. So this means that the angular displacement is defined as the change in angle theta. So you can measure this angle theta in radians. Right. So which means that as the particle will move around the circle, the angular displacement increases. Now this angular displacement is increasing at a steady rate, which means that this rate of change of angular displacement is defined as the angular velocity. So how does the angular displacement change with time is the angular velocity. So you can define it as the change in angular displacement divided by the time that it takes to change or cause this change in the angular displacement. So this is represented with omega. Angular velocity is denoted using omega. Now, moreover, we can now, because we have this angular velocity, we can do a comparison with linear velocity, right? So the comparison with the linear velocity is done so by coming back to this definition of angular velocity, which is delta theta by delta t is equal to the angular velocity, right? But we know if I look at this this circle, then angular displacement, which is theta, is defined as, or really delta theta is defined as this arc length from I to F. So I'll just write it as I, F, arc length, divided by this radius. So that's the angular displacement in radians. That's the reason we work in radians, because it's easier this way to work out some of the quantities or do some of the calculations in physics. So this would mean that the angular velocity is equal to this thing, which is delta theta divided by r divided by delta t. So, but what do we know about this thing? IF divided by delta t is simply the linear velocity, because IF is just the distance that it covers, right? IF is just the distance, and I divide this by delta t, and then I have this divided by r as well. So this part will give me linear velocity v. And then this linear velocity v is being divided by this thing r, which gives me a relation between v and omega. So we can see that v and omega are directly proportional with this thing that v is equal to r omega. So this radius of the circle is really the constant of proportionality between v and omega. So this gives us a very useful expression that will be very helpful while we are doing some of the calculations. So this means that if I have a body that is moving in a circle, then if I have its angular velocity, that at every point I can also compute its tangential or linear velocity, which is this v. So this v is given a name. Sometimes it's known as the linear velocity. Sometimes it's also known as the tangential velocity. Right. So it's not given this name as tangential velocity, by the way, because if you look at this circle, at every point on this circle, I can draw a tangent. So let's suppose you draw a tangent at this point F, there will be some velocity at this point V, which means that if this thing, for example, you could imagine that there is a string that has attached to this object, this ball, and then you whirl this string around like this, right? So the ball travels in the circle. Now, what happens if you cut the string? What will happen is that at whatever point on this circle we have this ball, it will start flying off tangential to that point with this tangential velocity v, right? So that's why it's given this name as tangential velocity. Right. So now let's imagine that you have a car and it travels around a circular bend. So for example, here, I'm going to draw this car with this circle, right? And it travels around a circular bend. So suppose maybe it looks something like this. And suppose that the radius of the circular bend is 24 meters. So here is the center, and the radius for this bend is 24 meters. Now the car is traveling at a constant speed. So the speed of the car, now if it says that it's 20, or let's just say that it's 15 meters per second. Now, if the speed of the car is given in meters per second, then obviously it is the tangential velocity. Because if we look back at omega, then omega is defined as this thing, the arc length IF divided by R divided by T, right? So the units for omega, or the dimensions of omega, are radians per second, right? So the arc length, which is measured, or the angles really, which is measured delta theta in radians divided by seconds, which is the units for time. All right, so this means that this velocity is the tangential velocity, right? Okay, good. So now if I were to compute the angular velocity of this car, which is moving on this circular bend, so that angular velocity with which it travels in a circle, that's the angular velocity, right? So we know that the angular velocity and the linear velocity is related with v equals r omega. So all I have to do really here is write this expression for omega, which would be omega equals v by r. Now, just putting in these values, linear velocity, which is 15 meters per second, divided by r, which is 24 meters, this gives you a value of 0.63 radians per second. So hopefully that makes the idea of linear velocity and angular velocity clear. So with that, we can move on to the topic of constant speed and constant acceleration, right? So we have constant speed, and let's just write it as this, constant acceleration. Now, so suppose that you have a body that moves at a constant speed around a circle. We know that the speed, although it might be constant, so for example, if I draw a circle and I say that I have a particle and it moves on this circle, right? Let's say that it moves like this. Now, suppose that I'm saying that its velocity is constant. It's moving with a constant velocity, which means that you would say that there would be no acceleration. However, remember, constant velocity would not be the case in this example. Why? Because we know velocity is something that is associated to the direction. Now, we know clearly, we can see that the direction at every point on this circle is different, right? So that means the velocity is not constant, but the speed is constant, because the magnitude of the velocity might be the same at every point on this circle. However, the direction is changing, which means that if you think about the definition of acceleration, it is defined as the change in velocity per unit time, right? But velocity is not changing with time, but the speed is changing, right? So again, velocity is a vector quantity, and so a change would happen in acceleration, right? Now, if I look at this diagram and I draw a vector diagram for this thing, so suppose that I have this particle at this point at some time, and it has a linear velocity, suppose that's v1. And suppose at this point, the linear velocity is some v2. Now, v1 and v2 are same in magnitude. So I can say that the magnitude of v1 is equal to the magnitude of v2. What makes them different is really the direction of these velocities, right? So then I can say that if I have this particle which moves on a circle, which is moving around a circle, at time t, it has this velocity v1, and at some other time t2, suppose that it has some other velocity v2, and the change in this time would be delta t, right? So this means that you can see that this vector, velocity vector, it is always towards the center of the circle. If you look at this circumference of the circle, the velocity vector is always going to be towards the center of the circle. So for example, let's draw this path as well, where it might be moving something like this. And let's call this one v3, and now just renaming these velocities. Here we have v2, right? So if I draw a vector diagram for v1 and v2, it would look something like this. So here I have v1, and here I have v2, right? So all I have done is taken this vector and placed it to the tail of this vector, right? Now the change in velocity vector would be something like this, right? So that's delta v. Now you can see that this is towards the center of the circle. Now as the body moves around this circle, the direction of the velocity is continuously changing, right? You can see that it's clearly evident. So the change is always happening towards the center of this circle. Now, this would mean that the particle has an acceleration, right? Acceleration vector is there, but it is of constant magnitude, but the direction is always towards the center of the circle. Now, because this acceleration is always going to be pointing towards the center of the circle, this is given a name as centripetal acceleration. Right. Now, the centripetal acceleration is given this name because the acceleration vector always points towards the center of the circle. So we can write a mathematical expression for this thing. So the centripetal acceleration magnitude, let's call it some a, and this is given as the, let's just write its magnitude as v squared by r, right? Now, if I use the definition, which we defined earlier as v equals r omega, we prove this. Now just use this in this thing, we get r squared omega squared in place of v squared divided by r, which is r omega squared. So that is the centripetal acceleration, both in terms of the angular velocity as well as the tangential velocity, right? So this just came from the original definition of acceleration, but we substituted for delta t in terms of the velocity and the radius, right? Okay, great. So now we can move on to the next topic, which is of, well, an obvious thing should be to move on after acceleration towards centripetal force, right? Now, centripetal force is, imagine that I have a body and suppose that it's moving in a circle. So let's see, I have, this is the center, and a body moves around the center in this circular path, right? So suppose it's moving like this. Right. Now, it is very important for you to realize that any body which is moving in this circular path is not in equilibrium state. It will not be in an equilibrium state simply because of the fact, as we saw earlier, that the acceleration vector is always going to be pointing towards the center, and so it's non-zero, even though the speed is constant. So there is a non-zero acceleration vector, right? So from Newton's laws, then we know that Newton's second law, really, we know that F is equal to ma. which really is just that the sum of all the forces that are acting on a body is going to give a rise to the acceleration, right? So this means that really a resultant force has to be acting on this body, with whatever body we have, which is moving in the circle. There must be a resultant force on this body, because we know that the acceleration is non-zero. So there must be something from here. Now, this resultant force that acts on the body is known as the centripetal force, which is really a force which is keeping this body towards the center of my circle. So it ensures that the body is in a circular orbit around this center. Now, this kind of force is going to have absolutely zero effect on the magnitude of the velocity, right? But it would be changing the direction. And so we know that because the acceleration vector over here is just the centripetal acceleration. It's not a linear acceleration. And we know that centripetal acceleration is only going to cause a change in direction, not the magnitude of the velocity, or the speed remains constant. So this means that I can use this expression and call this thing as the resultant force as some centripetal force, right? Which is equal to m. Now, this can be a centripetal force only if the acceleration vector is the centripetal acceleration, as you can see over here. So this means that in place of a, I'm going to substitute the centripetal acceleration, and I get, well, we have two forms of this. We can use v squared by r, which is mv squared by r, and this is the centripetal force in terms of a linear velocity. While this one, you can use the value for v, which is r omega, and here we have this thing squared divided by r, and so you get m r omega